Okay, let's do the problem set to decomposition forecasting. And here we have 2 years of data, and each year is divided into 3 4-month terms. The dependent variable is sales. And so maybe we can think of like a university that has a spring semester of 4 months and maybe a summer semester of 4 months and a fall semester of 4 months, and maybe that's the bookstore that whose sales we examine. Okay, so in the first step, let's actually calculate, or let's plot the data. So observation 1, which is year 1, first 4-month term, like spring, we have sales of 2. Then in the second observation, like the summer term of year 1, we have 6. Then in the third term, which is the fall, if it's a university, we have 7. And then we move to the second year, we are again in spring, and now we have only 1. So it would be here. But then in the second 4-month term, we have 8. So we would be here. And the final term, fall of year 2, that's an observation of 9. Okay. So that's the scatter plot, and yeah, that's actually quite interesting. So let's see how we would estimate that one. So what would that look like? Yeah, let's first combine the dots maybe. Okay, so we have this, then we connect this, then okay. So this is the data. So it's actually not that easy to fit a line of best fit, but let's try it. And then we can also always check Excel. So let's insert a line of best fit. I don't know, maybe something like this. So okay, so that's as good as I can get. Okay, so it looks like that the intercept is maybe 3 at point 1, maybe the slope is 1, so the intercept would actually be at 0, maybe 2. Okay, but anyhow, what we can see is if this is really the line of best fit, we obviously have a cyclical pattern. So if the first observation is indeed the spring semester, we seem to be below the trend line. And then the summer and fall, we are above the trend line. Then again, in the first semester of the second year, we are below the trend line, and then we are again above the trend line. Okay, so we would estimate a slope of maybe 1 and then an intercept probably of 2. And again, we don't start at 1, normally we start at 0. So, okay, well, let's see what the data says, or what Excel says. And we only look at the sales, so our independent variable is just like we number the periods just from 1 to 6 in this case. Okay, so we know that for our data we have the intercept and we have the slope, and we typically begin with the slope covariance. So we have the covariance between x and y. Divided by the variance of x. Alright, and let's see what we get. Okay, 1. So now what's the intercept? So the intercept is y bar, the average of the sales, minus the slope times x bar. Well, that's spill, so that's a clear indicator that I forgot something like average. Okay, so now the formula seems right. Okay, so the intercept is 2. Okay. So it looks like we fitted a line perfectly, and we can see if we try to forecast now the next observations, that would completely ignore the cyclicality. But in order to capture the cyclicality, we nevertheless need the trend line. So let's calculate next y hat, the predicted value of the sales, or maybe sales hat, or sales predicted. And that would be equal to the intercept plus the slope times, actually let's just spell it out because I may delete that later when we have the forecast period. So I'll just write 2 plus 1 times the observation, and I can delete this calculation. And now I have one forecast period, 7, 8, and 9. Okay. So now I can forecast the linear trend into the forecast period, period 7, 8, and 9, so year 3. Okay. And again, this will ignore the cyclicality, so we need to calculate next the difference between the actual sales, not the difference, the ratio, and the sales predicted. And we do that for the 2 years. So we divide sales by the predicted. And then we see that indeed in the first period, so observation 1 would be spring of year 1, so we are roughly 33% below the trend line. And then in the summer and the fall we are always above. Then in the next period, in the next spring, we are again below the trend line, and in the summer and the fall we are again above the trend line. Okay, so now what we do, we have to average that out and calculate the seasonal index. So the seasonal index so now we calculate first the seasonal index for the spring semesters, so of which we have 2. So now we calculate the average of the 0.67 and the 0.17. Okay, so that suggests that in every spring, on average, from the available data, we are 58% below the trend line. So now I can copy that to the next 2 observations, and that means the 1.32 that says on average, whenever the summer semester takes place, the bookstore has 32% more sales than what the linear trend line would predict. And in the fall, it's still on average 1.26. Okay, so then we can next use this data, and we just assume that this is always the same for all the next years. I mean, it's the best guess that we can have. So now when I copy this one, I need to make sure that I paste values, and then I copy this again for the next year, and then I remove again some of those decimals and limit it to maybe 3. It's good enough. Okay, so now we know the seasonal indices and how they relate to the linear trend line. So that means our decomposition forecast is equal to the predicted value times the seasonal index. Okay, so the trend line would predict 3, but the seasonal index brought it down to 1.25. Okay, now I just can copy this down. Let's remove some decimals again. Okay, 3 is enough. And so now let's take a look at it. So let's make a nice graph where we have the observations on the x-axis, maybe the actual sales, maybe the trend line. We don't want to display the ratio of sales to sales predicted and the seasonal index, but definitely the decomposition forecast. So let's insert recommended chart, all charts, line. Yeah, that looks nice. Okay. So this is, we don't need header. We know that here we have on the x-axis we have the period, so but let's clean that up a little bit and say maybe we want vertical grid lines. That always looks good. And on the y-axis I don't want a major unit of 2, but maybe only 1. And so here the blue line is the actual sales, the green is the decomposition forecast, and the orange line is the linear trend line. So maybe we can match it our graph. So the trend line, typically do it in black and we dash it, and maybe a little bit thicker. Then the actual sales, let's also fit it maybe at the marker, maybe a dot. Okay, maybe that's a little small dot. So I go a little bit bigger. Okay, so blue, but it actually made that red. And the marker red 2. Marker options, type, fill, solid fill. Let's make it red. And no border. Okay, violet and red. Again, marker option, fill, solid fill. Okay, so now we got it, but now we want to still remove the border line, no line. I mean marker, no line. Okay, so now it looks pretty close to what we had. And yeah, and the green is the decomposition forecast. And we can also add again the bubbles, no, the line markers. So marker option, built in, but also maybe a little bit bigger. But here we want a solid fill. Let's do it some green and no fill. Marker, solid fill. And the line, automatic color. This one here. Okay, so that's a pretty nice graph. I hope you can see it. And it's obviously clear that the decomposition forecast is a much better fit to the real data. And in order to measure that fit, we calculate the MAPE, the mean average percentage error. And for this, we need to first calculate the absolute difference between the actual minus the forecast. Why is that not? Actual minus forecast divided by the actual. And in an Excel language, that's absolute equals absolute. Okay, so I need another parentheses. Okay, so I take a look at the difference between the decomposition forecast and the actual sales. Divide by the actual sales. Oh, I forgot to close the parentheses, but Excel is small enough and figured it out. Okay, and of course I can only do that for the first 6 observations, so the 2 years. And then we can calculate the average. Okay, and then the MAPE based on the decomposition forecast is equal to the average of all those absolute percentage deviations. Okay, so it's 0.395. It looks okay. So if we do the same for the linear trend line, that should be actually much worse. So this was decomposition forecast, and if we calculate the same, the absolute difference between the predicted sales minus the actual sales divided by the actual sales. Okay, so here you see it's 50% because the trend line is much further away from the actual value than the decomposition forecast. So okay, let's limit everything to 3. And of course that would be the regular linear regression line. Just call that linear regression. So what is the MAPE of the linear regression? Well, that would be equal to the average of all these values and you see the average is more than 100%, largely driven by the fourth observation, obviously. So again we see that the decomposition forecasting is a much better predictor than a linear trend line. Okay, so now we can fill in the value. So we have the predicted y hats. So let's put that in here. And right click. Then the value over the predicted. The seasonal indices. And again, I make the first 3 bold because those are the actual, the ones that are being calculated from the average of the available value over y hat, and then they are just duplicated. And then we have the decomposition forecast. And we have the absolute percentage error, and this is only with respect to the decomposition forecast. Oops. And then we said the MAPE was equal to 0.395. Alright, so that's it. So do we have everything? We checked everything already using Excel. The mean absolute percentage error is 0.395. And we did the decomposition forecast. We filled out the table. So yeah, that's it. Okay, so I hope that this explains decomposition forecasting, and yeah, so that pretty much concludes also the lecture on decomposition forecasting. So yeah, thanks a lot for watching.